Okay, so let's get started. My name is Amal Ahmed. I'm going to be talking about logical relations and compiler verification in these 4 lectures. So I thought that basically my plan for this is that I want to spend the first couple of days talking about logical relations and the second 2 days talking about how logical relations can be used in the context of proving compiler correctness. Proving some simple compiler transformation correct. So, so this has been a sort of different OPLSS in the sense that I at least get the sense that you guys have seen logical relations from various angles in, some certain ways from a categorical perspective from Paddy. Sort of earlier, you've seen logical relations for simply typed lambda calculus that Dan Licata covered, right? And he showed you how that logical relation corresponds to contextual equivalence for the simply typed lambda calculus, right? So you've had sort of a basic feel of all of these things. What I'd like to do is sort of talk about applications of logical relations. So I'm going to start off with a perspective on okay, what are logical relations and what are they good for, all the various things that they're good for. And one of the big things that I feel that I want to get across in these 4 lectures is, so typically PL students are taught, okay, logical relations, parametricity, free theorems, system F, okay? All for terminating languages, which is very nice. You get very nice, pretty free theorems out of these, out of using this proof method. But if you look at the research that I've been doing, I think that they're good for so much more than that. In particular, I'm a big proponent of using this really elegant and powerful proof method in, for very realistic kinds of applications. So in particular, I'd like to give you a sense of how this method scales up to realistic languages. Languages that don't terminate, languages that have recursive types, languages that have mutable references, though I haven't decided if that's what I'll cover tomorrow. And so on. And then, that's what leads into the compiler correctness lectures that I want to do on Thursday and Friday. Okay, so that's just sort of to give you a sense of the perspective that I want to bring to these lectures. Okay, so logical relations are a proof method for proving a wide variety of properties. And yet I believe this week you have only seen what I would call binary logical relations. Logical relations that relate to expressions. Am I right? Okay. All right. But they're good for lots of other things too. Like the simplest form of logical relations that you might see, for instance, in Benjamin Pierce's TAPL, where their logical relations are used to prove normalization for the simply typed lambda calculus. Okay? So if we just talk about the kinds of things you can do with these, proving normalization for the simply typed lambda calculus. Okay. Yeah.
Is the material available somewhere? I just want to make sure if it makes sense to copy everything down.
So I can provide you with a set of notes, but you feel free to take notes too. Yeah. Okay. And this holds true for maybe today and tomorrow more than it does for the next 2 lectures. All right. Okay. So normalization says that any closed term of the simply typed lambda calculus will always terminate, okay? And this is a classic thing that you can prove using logical relations. But in particular, here you are interested in proving a property about a single term. You're interested in proving something like, if I have a well-typed closed term E in the simply typed lambda calculus, then it must be the case that when I run E, I'll write it like this, E terminates, okay? That's the property. Notice how it's a property of a single term, not of 2 terms. You can prove this using logical relations, but the kinds of logical relations you use for that would be a unary logical relation. Okay? And I'll talk about this a little bit more in a minute or 2. Another thing you can use logical relations for is to prove type safety. Does that come as a surprise to people? How do people normally prove type safety? Progress and preservation. All right, so today's lecture is going to be, hey, let's prove type safety, not using progress and preservation, okay? Today's lecture is all going to be about simply typed lambda calculus with recursive types. Let's use a unary logical relation to prove type safety, okay? That'll be the meat of today. All right, so What else? And of course then, okay, let's say binary logical relations. Logical relations are used to prove equivalence of programs. And now any kind of property where, some sort of relationship between two programs or equivalence between two programs is something that you care about, you can use logical relations to prove that. So what are examples of that? Things like representation independence, where you want to show that if you have two packages that implement the same existential type, right? Two implementations of the same interface, essentially. You want to prove that these two implementations are equivalent, you can use a binary logical relation, one that actually talks about relationships between two programs, not just one anymore. What else? Compiler correctness. So let's talk about compiler optimizations first, right? And within a compiler, you might have a certain intermediate representation of the compiler, some intermediate language, and you want to prove certain optimizations correct. So for that intermediate language, if you can set up a logical relation that lets you talk about equivalence, you can then use that logical relation, that proof method, to prove that your unoptimized program, the original one, is equivalent to whatever is being produced by your optimization, right? And that's a way of proving compiler optimization is correct. But that's still within one language, right? You can also use logical relations to talk about equivalence across two different languages. And this again, compilers are a perfect instance for this. So suppose that you have a compiler, this time I'll use the word transformation, not optimization within the same language, but a transformation from let's say from the source language of the compiler to perhaps the first intermediate language of a compiler, right? Or from the first intermediate language to the next one, or so on, right? So a transformation that goes from one language to a different one. And you want to prove that the original program is equivalent to the transformed program, which is now in a different language. You can set up a relation between programs in language 1 and language 2 and use that relation, that logical relation, to prove that these are equivalent. And therefore, that becomes a technique of proving compilers correct, right? You can imagine that a compiler is something that does sort of cross-language transformations in some passes, does some inter-language optimizations in other passes, and keeps going further and further down. If you could set up logical relations for every single one of those passes, this becomes a very nice compositional technique for proving compiler correctness. Now, I said compositional, and I sort of did this air quote thing. I'll get into this in my last two lectures, but basically, logical relations give you a way of talking about correctness of components, not just whole programs. That is one of the biggest reasons why they are really powerful and useful methods. Okay, and we'll come back to this point. All right, so equivalence of programs. A lot falls in that category. Now let's see, what else? Security type languages. Do people know what security type languages are? Languages which have type systems for information flow control, right? So just to give you a small example, in a language such as that, you would be able to do something like, say, specify confidentiality levels on your data. So I can say I have a variable x in a security type language. It is of type int. It is of high security. That's what the h indicates. All right? And I might have another variable, let's say y. Maybe it's also an integer, but it's low. All right? So what I have in mind here when I write programs in such a security type language is that I'm trying to say I have some high security data that I want to remain confidential, and I have some low security data. And this is observable by anyone, and I don't care. Right? But what I want to prevent by writing programs in such security type languages is I want to make sure that high security data never leaks out to low security variables or observers. All right? And basically, security type languages are purporting to give you a type system which is capable of checking that and guaranteeing that. If your program type checks, you know you have no leaks of confidential data from high to low. Okay? So, for example, if in my program I now decide to say that something like, I shouldn't say x equals. Suppose I say y equals x. So I'm assigning this high security data to a low security variable. This is definitely a leak, right? If my program decides to return y, this low security value, then my high security data has been leaked out, right? So a type system for a security type language would catch this and say, sorry, this does not type check. So this is what we call an explicit flow of high security data into low. You might also have something like just using an if then else. Suppose that you say if x is greater than 0, then do something like y equals 1, otherwise y equals 0. All right? What am I doing there? It's an implicit flow of high security data, right? So I'm letting the low security observer, think of that as y, observe something about my high security data. So my low security observer now can at least see that, oh, this confidential data, I know whether it's greater than 0 or not, right? So there is some amount of data that's leaking out. So this is an implicit flow of data. And a security type system would catch this as well. So this program would not type check. Okay, so all right, so people have been designing these languages, these type systems for catching, for basically ensuring information flow security. But once you design this type system, how do you know it does what you say it does? Right? I'm sure many of you know the answer who are familiar with security type languages. All right? But it's not just a matter of proving type safety for this language. I've designed a type system, I go and prove type safety. Right? Progress and preservation, all good. What does type safety say? Well, you can use progress and preservation to prove it. What does type safety say? It doesn't get stuck. Type safety says that if you have a closed program and it is well typed, of type tau, if I have a closed program of type tau, then it doesn't get stuck, right? I'll write it as safe. And by this I mean that E can either, when you run it for however many steps, either you've managed to reduce it to a value, or it can take another step. Well-typed programs don't go wrong, or well-typed programs don't get stuck. That's the slogan due to Robin Milner, right? Okay, well that's type safety. Coming back to my security type language, I've designed this type system, I've given it to you, and I claim that it catches all leaks of confidential data. How do you know whether to believe me? What theorem do I have to prove is what I'm saying. Sorry? Completeness how? Yeah. Basically okay, let's sort of intuitively get at what we want to say. Basically we want to say, let's take a program P, okay? If P was just some program in the security type language, and I wanted, I'm going to sort of assume that P is something that takes maybe a low security integer, just as an example, and a high security integer, and gives me back that, okay? And you can take an arbitrary program that takes some number of low security inputs and some number of high security inputs, think of these two as representatives of those, and gives you some number of low security outputs, and maybe even some high ones, but I don't want to talk about those right now. Okay, so the property that I want is the following, that if I run P twice, once with, let's say, some input, V low, okay, and some other input, V high, I should get the same sort of low security, equivalent low security outputs as if I run P with the same exact low security input, VL, but a completely different high security input, VH prime. That these two should produce equivalent answers. What does that mean? Yes?
It means that the two programs are indistinguishable to someone with access to low security data.
Exactly, right? The two programs are indistinguishable to someone who can only observe the low security data, right? And it's saying that those low security outputs that I'm saying this program produces are independent of, cannot depend on the high security inputs or any of the high security data inside the program, okay? Low security outputs cannot depend on high security data. That's the property you want from an information flow security type system, right? If that's what you're claiming your type system gives you. Yes?
But what if they take different numbers of steps?
Ah, very good point. So generally, if you look at the literature, if I were to go and design some language for information flow security, a type system, we don't count steps as an observable. But that's a very good point. you know, counting, so if you move from the PL community into the security community, right, the security community cares very much about, you know, what are the different ways in which an attacker can observe differences, right, or can observe something about your program. And security researchers will always bring in what we call side channel attacks, all right? Their model of an attacker, it takes into account things like, I can observe how long the program is running. We PL people, we often ignore that. We'll come back to that point later. Number of steps, energy consumed by a program, things like that, memory consumed by a program, et cetera. Yes? Ah, that's a good point. So, if you look at the literature, you know, different papers will state their assumptions and basically say, you know, we're assuming a deterministic model of computation. Those will be the simpler sort of things. And then, you know, there will be others where you are proving this sort of an equivalence up to some, you know, sort of probabilistic bound. That's when you are taking randomness into consideration. Yes. So basically, I'm trying to say that you still prove that there's some sort of property like this, which says low does not depend on high, but then it becomes a probabilistic guarantee. Okay? Those are harder to prove, obviously. More probabilistic, whatever, math involved. Okay. All right, so this property in the security type literature is called non-interference. It is a standard lemma that we prove whenever someone designs one of these information flow security type systems, right? But notice, the reason that I'm putting it up on the board is I want you to notice that this is a property that cannot be stated by just talking about one run of the program. P is the same program on both sides. I'm not talking about two different programs, but I'm talking about two different runs of the program on different inputs, right? This is what I call a binary or a relational property. It is not a unary property, okay? So in order to prove things like non-interference, you can again use logical relations, right? So this is another instance, in addition to compiler correctness and other things, where this kind of proof method is useful, right? Okay, all right. So there are lots of other uses of logical relations in the literature too, but I think that sort of sets the stage enough that I'd like to kind of talk about it. Oh, actually, let me talk about binary versus unary. Let's make this a little bit more formal. So when we say, usually, you'll notice that in the literature, the term logical predicates or unary logical relations is used when you are interested in proving some property of programs, but you're only interested in one run, so to speak, okay? Versus logical predicates versus logical relations, and by these I mean the binary logical relations that relate two different runs of a program, okay? All right. And so now we can sort of start to get a little bit more formal. So the idea, when you are interested in proving a property that is about one run of a program, you normally, so the term relation says you normally set up a relation, right? Here you set up a unary relation. So let's call it P for predicate. Right? You set up a relation, and you say, when do program terms, E, belong to that relation? And you normally index these relations by a type, tau. Okay? So you set up a logical predicate P that gives a specification of which E's of type tau, roughly speaking, should belong to the relation. Okay? Similarly, when you're trying to prove properties, binary properties, you will set up a binary relation that relates an E1 and an E2, and you again set up these relations, these specifications, by keeping in mind that I want an E1 and an E2 of type tau. I want to specify exactly when they're related. Okay? This is a very abstract specification, but that's sort of the broad map in which this proof method lives. Okay? So, and again, just to summarize, unary properties, something like normalization and type safety fall under, you would set up logical predicates, and things like compiler correctness, whether they're cross-language or single language, parametricity results, representation independence results, where you want to show two implementations of an ADT are equivalent, non-interference, etc., all fall under the binary logical relations. Okay? So, let's start to kind of make things more concrete. So I said that I want to talk about type safety today for simply type lambda calculus with recursive types. So let's move towards that. And actually, before I do that, let me broadly tell you what my plan is for these 4 lectures. So today we're going to do type safety, SDLC plus recursive types, mu. Tomorrow is a little bit up in the air. I was polling you guys right before the lecture started, right? So I was thinking that I would cover mutable references, which are another example of those, very realistic language features that are actually very, very hard to deal with logical relations. Like setting up a logical relation for a terminating language is very, very easy. Setting up logical relations for languages that don't terminate, that have recursive types, that have these interesting circularities, like with mutable references. Like when you have ML-style references, you can set up cycles in your heap. Cycles are a problem. Cycles are the problem. Cycles of various sorts. Okay. So maybe tomorrow I'll do mutable references, but maybe I'll instead do, because many of you said maybe I should instead just do examples of free theorems and so on. We will talk about that. Okay. And then in lectures 3 and 4, I'd like to talk about compiler correctness. In particular, I'm going to take a very specific example of a compiler transformation. We'll do typed closure conversion. This is the pass in the compiler where if you start off with a functional language, you do closure conversion. It means that you take all your lambdas and you transform them into closures that contain no free variables. Okay, we'll look at that transformation and how to do a type preserving transformation in particular. And we'll talk about how to prove it correct using a logical relation that actually relates terms in 2 different languages. Our source will be simply type lambda calculus, and our target will be system F with existential types. Okay? And then in lecture 4, I'll sort of continue with that theme, but I'll talk about more state-of-the-art in what is compositional compiler correctness right now. Like, how should we be stating compiler correctness theorems so that we can talk about not just, oh, I'm giving you a compiler correctness theorem that says you can compile code from this language down and then link with code that comes from the same language. How do we scale this to giving someone guarantees about compiler correctness when that compiled code might need to be linked with code that comes from other languages? It's a really, really interesting problem. So we'll talk about that in lecture 4. Okay? So more multi-language kinds of issues. And again, my goal is to keep it all simple and to give you the essence of how logical relations can be used in all of these techniques and how do you think about these things. All right? Okay, so that's the plan. So let's jump to type safety for today. Okay, someone's already told me what type safety is. Well-typed programs don't get stuck, right? Let's spell it out. Let's write it in a more mathematical way. And now we're going to start working with the simply typed lambda calculus that's up on the board. And shortly, I will add recursive types to that language. Okay? But first, let's just try setting up a logical relation to prove type safety for the simply typed lambda calculus. So what is type safety? I'll write the English. You have to think about the math. Well-typed programs don't. I'll say get stuck. Milner's slogan is don't go wrong. So how do I say that? I've already hinted at it. Oh, it's on the other board. If E is a closed program of type T, what do I want to say? Okay. So if E is a well-typed closed program, and E takes, let me say, some number of steps to E prime, and doesn't matter how many, some number, then either that E prime is a value, or there exists another E prime, such that E prime can take one more step. Yes?
Do we also need that E prime is of type stop?
Ah, you're thinking preservation. my question. You know, I think this is partly what I'm trying to tease apart here. We don't actually, for just what is the definition of type safety, I claim that we do not need to know that that E double prime or E prime is of type tau. We really couldn't care less. If all we care about is this property, well-typed programs don't get stuck, then this expresses that. Now, usually, I'm sure most of you have never seen a proof of this carried out without knowing that when you take these steps, the program that you step to also has that same type. That's because you have all been doing this proof using progress and preservation. Okay? Let's write down the statements of progress and preservation and see how those two together actually give us this theorem. I'm trying to express that this is the real theorem that we care about. Progress and preservation are just lemmas that we use in order to prove the type safety theorem. Okay? And since progress and preservation has been around since about 92 or 94, we have forgotten this. To be honest, most students don't even think about it anymore. By the way, Matthias Formalizing is down the hall from me. He who invented progress and preservation. All right. But maybe I won't get into critiques of that. He actually thinks that maybe we need a different technique. Anyway. Okay, so how do we state progress? What does the progress lemma say? If E is a well-typed program, then we can take another step, right? E is a closed, well-typed program. Then either E is a value or there exists an E prime such that E can step to E prime. Notice how progress talks about just one step, right? Whereas my type safety theorem at the top is much more general. It's saying, I care about absence of stuckness. Run for however long you want, wherever you are. You're either a value or you can take another step. That's what the top says, right? The bottom has sort of narrowed its focus much more, right? Progress is saying, okay, well-typed program, it's either a value or you can take one more step. All right, what does preservation say? If E is a well-typed closed program, and it takes a step to E prime, yes, then our E prime is well-typed and has that same type tau. Okay, at least for simply typed lambda calculus, that's how we say it, right? Okay, so is it completely obvious to people how progress and preservation together give us type soundness, right? It's a ping pong thing, right? You basically, if you want to prove this, and you're saying, okay, however many steps, right? So you assume that E is a well-typed program, and you assume that it takes some number of steps to E prime. Now you have to show something about E prime, right? So what you can do is you can essentially you can do a induction on the length of this reduction sequence, right? And say that, okay, for every single step that you're taking along the way, progress says I can take another step, right? Preservation says that my new term will have the same type. So after you've taken all of these many steps, now you know, by progress and preservation combined, that E prime will have type tau, right? And now you need to show that it's a value or this, and that follows immediately by progress applied to now this E prime, right? But basically the idea is a ping-ponging kind of idea, right? The two things put together give you this stronger theorem up there, right? Okay. No, there's one other thing I want to notice, even though this is a digression, but in order to prove type safety using progress and preservation, all of your intermediate terms of your program have to be well typed. You have to be able to build typing derivations for those intermediate programs. This is not something we ever notice or even, ever notice for simply typed lambda calculus. But when you have complex languages which have perhaps a lot of internal state, then you may not be able, your programmer may never be able to write surface programs. As in, I'm trying to say there's a distinction between surface programs that your programmer can write and the programs that arise once your program starts running. Certain locations might get allocated, for taking the simplest example of this, right? In ML, do you ever actually write a location L in your program? No, that is something you write, create a new ref cell, right? It's when the program is running that that location L suddenly gets generated. And if you're doing a proof by progress and preservation, you have to be able to type check L. Okay? This is a tiny little distinction, but it helps to sort of make sense of the universe in some sense when you're trying to do, scale these ideas to more realistic languages. Okay? So progress and preservation demands that you be able to build typing derivations for running programs. But notice that this type safety theorem doesn't care. It doesn't need you to do that. So I'm sort of trying to say that if you just had a surface language and you could type check programs in your surface language, if you were not using progress and preservation to prove type safety, maybe you won't have to write down typing rules that are able to type check running programs. And that's exactly what we can do with logical relations. I'm not saying it's the absolute great benefit, it's an observation. Okay? Sometimes it might be a benefit if it's really hard to build typing derivations for running programs. Okay, so let's get to it. How do we prove type safety using a logical relation? So we're not going to do progress and preservation, right? Okay, so as I said before, the idea, we're going to set up a unary logical relation because type safety is about a single run of a program, right? So we're going to set up some sort of a predicate, a unary relation, on terms E of type T. And I'll modify that a little bit. You don't always set up these relations on, terms that actually have type T, like for which you can actually build this derivation. Sometimes you use this kind of method, and the terms that you put into these relations look like they have type T. You may not necessarily be able to build a typing derivation for them. Okay? I'll just put that out there, and we'll come back to it when we see a better example of it. All right. So here's the idea. When we set up a relation, right, I'm trying to characterize logical relations for you as an arbitrary proof method. And type safety for me right now is just one instance of a property that I am interested in proving. And I'm going to use a unary logical relation in order to prove it. Okay? So when we do that, let me just find. What we're interested in doing is we have to build these logical relations with three things in mind. First, you're going to build these relations so that they're indexed by this type tau. Okay, so the relation is going to be defined by induction on the type tau, which means that for simply type lambda calculus, we're going to have one case for Booleans, and we're going to have one case for tau 1 or tau 2 function types. And that's all I've put on the board so far, so that's all we have to deal with. When we add recursive types, we'll have one more case for recursive types. Okay? All right, so built by induction on the structure of the type tau. What do you put in the relations? Well, as I said, normally you put in terms that look like they have type tau. Right? So now let's start to make this more concrete. And actually, I'm going to do one other simplification. I'm going to split up building this relation so that I have, essentially, instead of just defining a PE, I'm going to define a P relation for values, and I'm going to define sort of an E relation for expressions. I'm just going to tease apart the value and expression cases because this makes your life easier. Okay? All right. So let's do that here. I'm going to write V for my value relation. So at the type Boolean, what values look like they have type tau, have type Boolean? True and false. Okay. How about functions? What values look like they have type tau 1 arrow tau 2? Lambdas?
Lambdas with some x and some.
Right, so some sort of a lambda, right? And this should be a tau 1 so that it matches this, right? This is simply typed lambda calculus. I have an annotation on my lambdas. I'll leave it there. Okay, so lambdas look like they have that. Yes? Conditionals. Okay, so far I was just asking for value forms. By the way, we're going to need conditions there, so we'll come back to that. a conditional and if then else expression is an expression. So I'm going to put them into my E relation, okay? Which is going to say, when do expressions, roughly speaking, expressions that we hope have type tau, belong to this E relation, which I'm now going to index by the type tau. Now notice I'm not going to build an E for bool and an E for tau 1 or tau 2. This is why I said that this just makes your life easier. It collapses a whole bunch of things into one condition, into one part of the specification. Okay, so now I want to say something like, an arbitrary expression E, by the way, that I'm hoping has type tau, you know, for type safety reasons, right? Or behaves like it has type tau. Some expression E belongs to this relation. Now again, keep in mind that we're building a relation here into which we want to put in expressions and values that have the property of interest. If I was proving normalization, I would, when I put things into the specification, into these relations, I will try to make sure that they have the property of interest. If it was normalization, I would say E belongs to E of tau if E terminates. That's literally what I would write here. Today we're doing type safety. So I want to say that E belongs to this type if what? Sorry, say that again? If it can be assigned a type tau. Hold on. What is our property of interest? No, we don't want termination. I want less than that. I just want type safety. So it would be termination if I was interested in proving normalization. I've decided to just do type safety today. So then it don't get stuck, right? Okay, maybe we should spell out those stuff. I'll write safe E here. That's our property of interest, okay? And safe E says that that no matter, it basically says this, that no matter how many steps you take, you get to either a value or you can take another step, all right? But I'll sort of spell it out a little bit more carefully. So safe E says that for all E prime such that E can take some number of steps to E prime, if that's the case, then E prime is a value, or there exists another E double prime such that E prime can step to E double prime, okay? Basically, look, right there, my property of interest, right? I could have written type safety. I can now erase this stuff and just write safe E, right? I'm trying to say the type safety theorem that we're interested in proving says if E is well typed, then safe E. Yes? Yeah? No, why do you care? That's true, but it's not what we traditionally understand type safety to mean. So if you agree with me that we want type safety to just be an absence of stuckness, then you don't care. And I completely agree with you. If you were interested in the stronger property, then I would modify this. It's just that I've sort of said, okay, this is what type safety means, and this is the property we want to prove. And if you want to prove the stronger property, you would just set things up a little bit differently. Yeah.
So this issue confused me too, but is this related to what you were saying about how we might introduce new locations that we don't know how to type check, and so you have intermediate values that actually won't type check and keep the guarantee?
Yes, exactly. So yeah, I mean, I think you guys are worrying about running this program and then the value, as you said, the value that you get out of it. How do I know it's the right value? Like when someone says type safety, perhaps you think not just this program won't get stuck, but you think, hey, I better get something sensible out of it if it does actually terminate, right? That would be nice. But that's not how we've defined it in the literature all these years, right? Type safety is really a much sort of deeper concern that I think when we say absence of stuckness or don't go wrong, these terms are so vague that they lose what we really want. What we want is we want all errors to be caught, right? So somewhere along the way, in a language like C, strange things might happen and just sort of arbitrarily, right? And then your program core dumps. We don't want core dumps. That's what type safety is saying, right? Don't get stuck. Don't core dump. right? No uncaught errors is kind of part of this. For example, ML is a safe language, but Scheme is a safe language too. It's just that Scheme is dynamically type safe, right? Scheme does not have a type system. C does not have a type system. But Scheme is dynamically type safe. It is a type safe language, whereas C is not. What is the distinction here? It's a very, very important one in the yes?
Scheme programming, it might error, but it won't crash.
It might error, which means that at runtime, if you do something which is utterly nonsensical, given the limited type system of the language, right? It will tell you, it will give you a runtime error right then and there. Unlike C, which will keep treating, you may have just tried to take a pointer and apply it to something as if it was a function. And it'll just keep running and keep trying to do its best until very far down the line where it does a core dump. That's the distinction, okay? Catching errors sort of faithfully. And in order for Scheme to catch errors in this way, a Scheme implementation has to keep a lot of tags around. It has to, remember that this thing is a function. It may not know that this is a function from, int arrow int to bool arrow bool or something like that. It doesn't have that level of, type information in the language, right? Because it's unityped, sort of. But it does keep around information that something is a function, or something is a string, or something is this other kind of data. Yes?
So I'm confused by this distinction between C and Scheme.
Yeah?
Because it really seems to me that it's a property of the C implementation that it core dumps.
Ah.
Like there are other implementations of the C language that behave the same way as Scheme does.
Okay, so let's say that it's a matter of language specification. I agree with you, actually, yes. But it's a matter of language specification. In order for you to be a faithful C implementation, you can core dump and still be a faithful C implementation. But you could be a better one, you're right? You could be implemented in a much better way and therefore be a better C, a safer C. Whereas the Scheme specification does not allow that. You cannot be an okay Scheme implementation if you core dump, if you don't catch errors properly at runtime. That's the distinction. And really, actually, I'm really glad you brought this up, because a lot of this often for us is a matter of the language specification, right? I'm talking about properties of languages. Like I gave you the example of security type languages. It's all about you claim you have a certain property, right? That is the specification. And then what do implementations do? Their role is to preserve that specification. As we compile, if your language specification says this program has this meaning, then me, the compiler, I have to faithfully preserve that as I compile to lower and lower level languages. But if you are so flexible and you allow undefined behavior, for instance, like C does, then I have much less to be faithful about. Frankly, it's easier to write a correct compiler, I think, for languages that are sort of less, tightly specified. We'll come back to that in 2 days. Good? Okay. So back to where we were. Any other questions along these lines? No? Yes?
So the definition of safe, do we certainly say that it includes the D as that file, or that's not?
In the definition of safe, you do not need these things. Actually, nowhere in safe do I even say that this E has type tau, right? Yeah. So basically what I'm trying to say is that the theorem we are interested in proving, type safety, says that if you have an E that is closed and has type tau, then that E is safe. Okay? All right. So E is the safe here is the property of interest, right? And if you were doing normalization, normalization would be the property of interest. Okay. So what I'm after here is basically to define. I want expressions E to belong to this relation when what? When they're safe. Okay? So the way that I'm going to do that is by saying, basically by writing the definition of safe in here. All right? Okay, I'll come back. Okay, so for all E prime, if E takes some number of steps and goes to E prime, and that E prime happens to be irreducible. It can't take another step. Okay? Now we don't know why it can't take another step. Maybe it's a value, which is good. Maybe it's stuck, which is bad. Right? Okay, so what we want to say is that if you reach some E prime and that E prime happens to be irreducible, then this is going to be one of the good situations. All right? It's going to be a value. So the E prime must belong to the good values that we have of type tau. Okay? So notice what's happening in this definition here. We're trying to build these value sets which say what are the good values? And then we're trying to build a set of safe expressions. So safe values, safe expressions, if you will. All right? Now, I've left a ... over here. When are lambdas safe? When they're safe for?
All things you can plug into them.
Yes, when they're safe for all inputs, right? So at the face of it, you could say a lambda is always safe, it's a value. But if you stop there, you're not going to be able to finish your proof. Okay? Essentially, in technical terms, your induction hypothesis won't be strong enough. All right? Okay, so for a lambda, and in general for value forms, we sometimes have to think about how is this value going to be used? And lambdas are used in a very interesting way. They are used, their elimination form is application, right? They're used by applying them. So good things have to happen when you apply them. All right? In particular, if the property of interest here is safety, then a lambda is safe when the elimination form for functions, application, preserves that safety property. Okay?
Say that again.
We want, I'll say the specific form and then I'll say the general form. The specific form is that a lambda is safe if when you apply it to all safe values, you get safe results. Okay? So let's write that. For all values v that I could apply this lambda to, and by the way, I said values v because, sorry, I didn't mention this before. I have simply type lambda calculus up there, but I have it with a call by value reduction strategy. If you notice my evaluation context, right? This is a call by value simply type lambda calculus. That's why I'm applying my lambda to a v. If this was call by name, here I would say for all expressions e that you wish to apply this lambda to. Right? Okay, but this is call by value, so I'm going to say for all values v that you apply this lambda to, as long as that v comes from the v relation at type tau 1, so you better give me a v that actually has the type that you say you want. Right? Notice we're interested in good behavior, right? Good behavior at a certain type. These terms have to behave like that, like the type that they're, that the relation is indexed by. So, a function looks like, I'm going to say looks like or behaves like it has type tau 1 or tau 2, if when you give it any value that looks like it has type tau 1, when you take that value and plug it into the body of the lambda, that looks like it is an expression of the result type tau 2. Okay? You give me a value that looks like it has type tau 1 and is safe at type tau 1. That's built in, right? Then I give you a result, that expression, after beta reduction, right? After we take a step, we take this lambda, we apply it to this input. What do we get? We get e with v for x in it, right? Right after beta reduction. That expression, which is going to run to our result, hopefully, if it terminates, that looks like or behaves like an expression of type, a safe expression of type tau 2. Okay? So there are all these sort of invariants that we're building in. Yes?
Is there a difference between saying that V has type tau 1 and that V belongs to that of those values?
Okay, I am making a distinction today, all right? Which is, I am defining these relations without requiring that I have a typing derivation for this. I'll come back to this issue later, because you can often build logical relations that actually, when you define these relations, you say, we're building the relation out of well-typed values, which means that you always require that if I'm putting e here, then it must be the case that e is a closed term of type tau. If I put a v here, then it must be the case that this thing is a closed lambda of type tau 1 or tau 2. We often do that. We don't do that for type safety because that would sort of defeat the purpose. Then I would need progress and preservation in order to prove type safety. Okay? I don't want to show you why. I just want you to trust me on that today. You can think of this also, for those who are familiar with the term, you can think of this as a realizability model. I am taking terms from my language and building them into these relations, and I'm going to prove to you that these terms, if you actually have a typing derivation for one of these terms, then the term will not get stuck because it belongs to the relation. That's the idea. Okay? So for now, don't assume that I actually have a typing derivation for the lambda that I have put here. Okay? But again, I keep saying looks like or behaves like, right? That's kind of key to my argument. That's why I only put true and false here and bool, for example. Yes?
So when you have a function application, does that have to be a value of that number?
You mean right here?
Yeah.
So this sort of decision is determined by what language you are creating this logical relation for. Since my language has a call by value reduction strategy, it means that I will, when I actually do, can you see that beta rule up there? Not quite. My language has lambda x colon tau dot e. That's the reduction rule, right? Since this is a call by value language, you have to get your argument down to a value before you can apply the lambda to it. If this was a call by name language, then my reduction rule would look like this. I would have an e prime there, right? And I would substitute e prime for x. For a call by name language like that, this would be wrong. The proof won't work. So you have to listen to your language when you build these things, all right? So basically what we have to do for a call by name language, we would have to say, for any e prime that belongs to the e relation at type tau 1, etc. Okay? This is another actually this is a good digression because when we build these things, one of my students recently said this, which was nice that he was saying it to me instead of me to him. You have to listen to the language. Okay? So yeah, you have to, a language is first specified in the sense that you write down the syntax, you write down the operational semantics, and you write down the typing rules. Now your language specification is complete. Now you move on to the step of, I want to prove properties about this language. That property might be type safety like it is today, or it might be properties about equivalence or non-interference or other things, right? When you go to prove those properties, you have to kind of, listen to what the language's behavior is, what its reduction rules are, and sort of build them accordingly into the relation. Otherwise, you won't get it right. Otherwise, your proofs won't go through. Okay, so let's switch this back for our call by value language. For all inputs v that look like they're safe and of type tau 1, once we plug that into our function body, we get a safe expression. Okay? Any other questions? All right. So, what do we have? I leave my notes in different places. Okay. All right. So, notice that, I didn't quite say this, but I'm building the value relation out of closed values. Okay? These don't have any free type variables in them. And this expression E is also one that is closed. All right? I could specify this on the side, but I'm just going to say it instead of putting it on the board. Okay? There are no free variables. All right. Now, let's talk about how we I claim that this is a logical relation, and we are going to use it to prove type safety. How are we going to do that? Well, so notice we want to prove that if some E is well typed, then it is safe, right? That's the thing of interest. Now, the way that these things get set up in the logical when you use logical relations is you are essentially interested in showing two things. Overall, you want, if something is well typed, then it has a property of interest. But you break it up into two parts. You say, if something is well typed, then it is in the logical relation at that type. Part 1, part A. And then part B, you prove that if something is in the relation that you have built at a certain, at whatever type, then it has the property of interest. Okay? Now notice, if we can prove A and B, we'll be done, right? Okay, now the magic is, well, proving these two things. Okay, and by the way, let's step back for a second. The reason that we ever set up logical relations is because you want to prove some property that you're interested in, but you don't have a strong enough induction hypothesis somewhere. Like usually, in the case of type safety, in the case of normalization, if you tried to just prove if E has type tau, then it's normalizing or it's safe, if you just tried to prove it by induction on this derivation, you would get stuck. And for something like the lambda calculus, you would get stuck at the function case. Basically, you will find that when you get to an E, which is a lambda, you don't know that the body of the lambda has the property of interest. And basically your induction hypothesis isn't strong enough. It tells you all sorts of things about the terms of your language, but it doesn't tell you anything about sort of these subterms that are living under the lambda that will only be exposed once you do an elimination form, once you apply the lambda to something. Okay? So the theme here is that these relations are set up when you need such a stronger induction hypothesis. And they are set up, now let's recap. They're set up with a few things in mind. You set up a relation so that inside the relations you put things which look like they have type tau, or you actually say that they have the type tau. You want the things you put in the relation to have the property of interest. You're going to engineer it and build it with that in mind. 3, you want, for things like lambda, you want at every single type, you want the elimination form for that type to preserve the property of interest. And that last one is really the big deal with logical relations, right? Logical relations come with a slogan, which says, if you give me, and the slogan is sort of all, you can tell anyone what the slogan is by pointing at the function rule normally. The slogan is, if you give me inputs with the property of interest, I will give you outputs with the property of interest. If you give me related inputs for binary logical relations, which capture equivalence, maybe, if you give me equivalent inputs, you get equivalent outputs. If you give me, whatever, generalized property of interest. Okay. Okay. So then you split up the proof that you're interested in, that well-typed terms have this property, into these two pieces. Now, let's prove part B. The logical relation is up there, right? How does being in that logical relation imply safety? Suppose I have an E. It belongs to the E relation of type tau. Definition's up there for you. We have to prove safe E, okay? So what do we have to do in order to prove safe E? We start out by saying, consider an arbitrary E prime such that our E steps to E prime, right? I'm going to be super methodical about this. Okay, consider an arbitrary E prime such that E steps in some number of steps to this E prime. And what do we have to show? That either E prime is a value or it can take another step, right? Okay, I won't write that down. Or maybe I will. Yes? What if what? Ah, it should work. You're absolutely right. Values are expressions in this language. So, let's see how it works. Okay, so let's see. That's what we have to show. And all we have, our hypothesis is just that this E that we're considering is in the E relation. All right, so now that E relation says that for any E prime such that E steps to it, oh good, we know that there is an E prime, that E steps to E prime in some number of steps. So you go instantiate that E relation with that, okay? And then it says, if it's irreducible, then I can tell you something about it. So let's consider two cases. Right here, we know that E steps to E prime, right? So there are two cases. Either E prime is irreducible. Or let's say it's not. Let's do the not case first. Well, let's write it as not irreducible E prime. If E prime is not irreducible, what does that mean? it means that there's another step, right? So we're done. Okay. Therefore, by definition, there exists an E double prime such that E can step to it. Okay, good. That's case 1. What is case 2? Case 2 is where our E prime is irreducible. And now what happens? Yes, up there it says, oh, if that E prime happens to be irreducible, then it's in the V relation. That means it's a value. We're done. That was super easy, right? That's because we built a relation very cleverly. I kept saying, build a relation so that the terms in it have the property of interest. Okay? All right. So proving part B is usually very easy. All the hard work gets put into proving part A. All right? And in fact, part A is not going to be provable as written. So let's move on to that. So let's prove part A. How would you prove it? What's the proof structure? If E is well typed, then we want to show that this expression E is in the E relation at type tau. What is the only premise you have? Yes, E is well typed. Okay, so when I say, so we have that E is well typed, right? That means we have a typing derivation for it. We have a big tree. Okay, so in order to prove this, what would you do induction on? Induction on typing derivation. Okay, all right. So proof is by induction on derivation. That derivation. Okay, all right. So we're going to consider all sorts of different cases. We're going to have one case for every single typing rule. So there are our typing rules, booleans, etc. Okay, now notice our E is closed, right? E is closed. We want to show that it's in the E relation at type tau, right? So one case for every typing rule. Let's do the super trivial one. When true is a boolean, we need to show true belongs to the E relation at type bool. Let's just quickly go through the mental steps of what happens there. Well, we have to show that it's in there, so we say, suppose that true takes an arbitrary number of steps and gets to some E prime that is irreducible. Now we have to show it's a value. Well, we know true is already a value, so it could never have taken any steps. So that E prime had to be true, and true is already in the V relation at bool, which is what we are required to show. Yeah? Okay, good. Same thing for false. Do you want me to do that more slowly? No? Okay, good. All right. Let's just get to the one that's going to be tricky. So suppose that we are doing the lambda case. Well, then what we have above the line is x colon tau, E has type tau 2. Right, that's what we have. Doing induction on the typing derivation. Anyone see a problem? Induction hypothesis, right, exactly. When in this case, where if we try to say by the induction hypothesis, the only thing that we can do induction on, right, we need to say by the induction hypothesis applied to the thing above the line. But the thing above the line doesn't match what we're working with. It has something in gamma. It does not have a closed environment. So we are trying to prove this theorem. Our induction hypothesis can only be applied to closed terms, and now we can't apply our induction hypothesis. We are utterly stuck, right? Okay, so you have to generalize the theorem that we're trying to prove. We cannot prove this for closed terms. Lambda's going to get in the way. So we have to do this for open terms. Okay? But what does this mean as written? It doesn't make sense because I told you that I built this E relation at type tau with closed terms. They don't have any free variables. So we have a bit of a conundrum. We have an E relation that only talks about when closed terms are safe. how do we lift this notion of safety up to open terms? Yes?
For any substitution, it would be in the form of the open type variable, open term variables in state.
Yes, okay.
Such that there's a type A, such that it would form a closed term.
Yes, yes, something like that, right? So basically you want to say, give me, let's do this actually for a really simple case, right? Let's just pretend for a second that our gamma only has one variable to really see what happens, right? So what we want is to define, I'll write it like this. We want to lift this logical relation notion up to open terms. This is not the normal typing turnstile. I'm defining a new relation, okay? I'm defining an open logical relation, or a logical relation for open terms which can have free variables. So imagine that I had an open term which only had one free variable. I'm asking you to imagine that E-type checks has some type tau prime under that, okay? So for that, what would be my sort of logical relation notion of, safety? That's what we're trying to capture. So I want to define some relation like this for open terms. And basically what he just said, what we want to do is say, give me some value with the right that has the property of interest at type tau. Okay? So we're going to say for all v that belong to the v relation at this type tau, because this is the v I want to plug in for my x. If you give me one of those, then E with v for x should also have the property of interest, but this time at the type tau prime. Notice how much it looks like lambda? Pretty much the same thing, right? Okay, so that's how we can lift it up to open terms. Only we need to do this for an arbitrary gamma, not for a single variable. All right, so let's do it properly now. This says, not that E is well typed syntactically speaking, or you can build a typing derivation for it. It does not say that. It says that E which is an open term, belongs to the logical relation at type tau. Once you close it off with good safe values substituted for all of the variables in gamma. Okay? So what we want to say is that for all substitutions, I'll write little gamma, that belong to some relation that we'll set up in a second for big gamma, I can take this substitution. By the way, this substitution, I want these substitutions gamma that are essentially mappings from variables to values. Okay? Only I will want to define this G relation for gamma in a way so that all the values that I have in the relation belong to the proper V tau. If gamma says X has type tau, then this V should be in V of tau. Okay, we'll do that in a second. So then we want to take this closing substitution, use it to close our program, and then we can just use our closed logical relation as before. And now let's define the G relation. Let's do it inductively on the structure of gamma. So gamma, if gamma is the empty environment, then what substitution do I want? Empty. And if gamma is that, then I want some sort of substitution gamma with an extra x maps to v. Think of this as an extension of that, such that this part of the gamma belongs to G of gamma, and the extra value that we've just added in behaves like something of type tau. And here we use our V relation again. Right? So the V and V relation are capturing the property of interest, and we constantly want to keep appealing to them whenever we want values or terms that have that property. Okay. So now what we've just done is lifted our notion, our logical relation, up to this, up to open terms, right? And really there was no magic here. All we did is we said, oh, we have an open term, we need to close it off. But we can't just close it off with garbage. We need to close it off with values that have the property of interest. Yeah, then it wouldn't work. Right? So we said, give me a substitution, and the substitution better map to values that all have the property of interest. And again, if this was called by name, we'd be doing E there, right? Yes? So I just said, so if this was a call by name language, our substitution would map to expressions, precisely. And then exactly like what I talked about for the lambda, here, E in the E relation, we would do the exact same thing here. The substitutions would map variables to expressions if this was a call by name language, and then we would have E in the E relation here. Yes, so it's very nice and symmetric how things shift depending on call by value versus call by name. Okay? All right. Okay, so now the theorem that we are going to prove says that if E is an open term that's well typed, then E is in the logical relation. Right, this is just a shorthand for saying all the... This is just a shorthand for saying, if you give me inputs with the property of interest, I give you outputs with the property of interest. Again, right? Okay. All right. So now we have to do the proof of part A, but things are going to go a little better. So we have an open term, and we're trying to show by induction on the derivation, this derivation. And notice the true case is just trivial. Why is the true case trivial? Maybe we should see it. What do we have to actually do? When we have true of type bool under gamma, what we're required to show, just to really spell it out at the outset, is that property. The true is in the logical relation, right? Which means that now, in order to show this, first thing you're going to do is say, consider arbitrary substitutions gamma that belong to G of gamma, right? And then you have to show, so have gamma in G of gamma, show, sorry, I'm spelling out really trivial things, but it's good to see the definitions unwound at least once. So you have to show that, right? But any substitution applied to true is just true, right? Which is equivalent to showing that true is an E of bool. And we already did that a minute ago as an exercise, right? Okay. All right, so let's do the lambda case now. So we have a lambda of type tau 1 or tau 2 under gamma, and its body type checks under that. Okay, let's kind of step through this. You guys want to step through this? Do you want to leave it as an exercise? Tell me how you're feeling. Do you want to do the proof of this case? Yes? Okay. All right. Okay, so what we have to show is that under gamma, this lambda x colon tau 1 dot E, belongs to the relation at type tau 1 or tau 2. Right? Okay, so again, let's just be super mechanical about it. We want to show this. First thing we do is we say, consider arbitrary substitutions gamma. And show that once you wrap your lambda with that, you get something that's in the E relation. There's one here. And what type? You're going to have to help me with the proof. It's almost 5 p.m. I want to make sure you're awake. Okay, so you have to show that. Now, the first thing we're going to do is we're going to push that substitution in. This is generally something that helps with every single case. Okay? So notice that this is equivalent to showing, let's be careful about this. This little gamma, its domain, the variables that it's mapped, are exactly the variables in this. Right? When I write gamma comma x here, I am assuming that that x does not appear in the gamma. The comma is like a disjointness requirement. Okay? So this gamma does not have x in it. All right, so I can push it in and do that, push the substitution in, and now I just have to show that this lambda belongs to the relation. Right? Okay, so let's proceed. We want to show that this lambda is in the E relation. What do we have to do? E relation says, well, consider arbitrary E prime such that this steps to E prime, and that E prime is irreducible. So we're going to consider arbitrary E prime such that this lambda steps to that E prime. Anyone want to say something at this point? The lambda can't take any steps. So if it steps to some E prime that is irreducible, that E prime must be equal to it. Right? Because it's a value. It can't take any steps. People with me? Should I write it out? No. Maybe I should write it out. I think I should write it out. Okay, so we want to show this, remember? Showing means you look at the statement and you say, okay, what do I have to show? You have to show for all E prime. So we say consider arbitrary E prime such that our lambda steps in however many steps to that E prime, and that E prime is irreducible, right? And then we have to show that that E prime belongs to V of tau 1 or tau 2. That's what just happened. But since this is a lambda and we're saying it steps to an E prime, lambda can't take any steps. So this must be 0 steps, and therefore E prime must be equal to lambda, right? Okay, therefore, what we have to show here is equivalent to having to show that the lambda x colon tau 1 dot gamma E belongs to V of type tau 1 or tau 2. Good? All right. Okay, so now we have to show the lambdas in the V relation. Let's look at the definition of the V relation. What does it say? It says in order to show that that lambda belongs to V of tau 1 or tau 2, you have to consider an arbitrary input. Okay, so we're going to consider an arbitrary V, our argument, that belongs to the V at the argument type, which is tau 1. And we have to show that the body of the lambda, which now is gamma E, right? We have to show that the body of the lambda gamma E with V substituted for X is in the E relation at, read off the definition. Which type? Tau 2. Okay. Now we have to show that. What do we do now? Induction hypothesis. Yes. Okay. What do we have by our induction hypothesis? No, I didn't do all this to get stuck again. We won't get stuck. Okay, so induction hypothesis. This time we can actually apply our induction hypothesis to the thing that we have above the line, right? So the derivation, this is a subderivation of the one that we were working on. Therefore, something has gotten smaller. We can apply our induction hypothesis to this. By the induction hypothesis applied to X colon tau 1, E colon tau 2, we have, I want you to really just think about what we have. What do we have? What's the theorem we're proving? Read off A. We have exactly this thing, but with a double turnstile here, right? Yes? Because our induction hypothesis tells us that if you have an E of some type, then that E is in the logical relation of that type. So what we have then is, we have this fact. Now let's see how to use it. How do we use one of these facts? Well, the definition says this. Some E at some type tau with some gamma in the logical relation. It says, if we can provide some substitution, if we can provide some sort of gamma prime substitution that belongs to G at this type, if we could do that, then we could take that gamma prime and wrap it around the E and so on. Right? How do you construct a substitution for gamma with x colon tau 1? Gamma with x maps to V. Which V? That V right there. Right. Okay, so let gamma prime be that. Right? And notice that gamma prime is in this G relation. Why? Because little gamma is in G of gamma, and the V is in V of tau 1 from here. Right? So we have this fact. Therefore, what we get from using this is that gamma prime wrapped around this E belongs to E at the type tau 2. Correct? If we expand this out, this is just gamma with x maps to V applied to E, which is gamma E with V for x. And therefore, we know now that this is in tau 2. That's what we needed to show. Yeah? Okay. All right. Questions? Yes? No, we didn't show it. This is the proof of it, right? Here, I was saying we are required to show. Anytime I put show and I underline it, it means that we have to show.
No, but we showed that thing because that's already a lambda. We know that cannot further be.
No, but this statement says this lambda belongs to V of tau 1 or tau 2. And that means that in order to show that that lambda is in this relation, we have to do what this relation asks. Right? So that means we have to show that our lambda, which is sitting down there, in order to show that it belongs to this relation, we have to show that this is true. That's what I just did, right? So we have to consider an arbitrary input in V tau 1, and we have to show that after substitution, the result is in tau 2, which is exactly what we did on that board. Right? Yeah? Yes? No, not at all. Other than the parts where I alerted you before, right? That you have to set up your substitutions for call by name have to have E's here. And actually, we didn't even see that yet. Once we get to the applications case, that's where whether you're doing call by value or call by name will affect something. Lambda, it didn't come up because lambda is already a value. We didn't do any reductions. In the application case, we will do reductions. Okay, so here's what I'd like to leave you guys with. I know that your hands-on session got moved to earlier today, but as an exercise, I'd like you to do the application case, right? And there you will find yourself doing reductions, and it's not utterly trivial, that proof. It requires some care. Okay, so what I'm saying basically is we've just done this case, right? Do the case for application where you have E1, E2, right? Basically for the application rule. It's up there somewhere. I don't have to write it out again. There, right? Your induction, by the induction hypothesis, you'll know that the E1 itself is in the logical relation, right, with the turnstile there, and you'll know that the E2 is in the logical relation, and then you'll have to use that to prove that after application you're in the logical relation. But that one's really interesting. Basically because you end up, I'll sort of just sketch it out for a second. You start off with a gamma substitution wrapped around the E1, E2, right? You'll know that gamma is in G of gamma, and you'll have to show this. Right? And now you're going to have to, sorry, I have a tau over there. Let me just put tau. In order to show this, you're going to say, okay, suppose that this term reduces to something irreducible, right? Now, back to your question. We are going to be talking about reductions because this term reduces. Now, the first thing you should do is push the substitution in, and notice that this is equivalent to gamma pushed in around both, okay? Equivalent to showing that. And then you'll be able to use your induction hypothesis. But now this is the case where you'll notice that you actually have to use the definition of the value relation of tau 1 or tau 2. And without it, you can't complete the proof. And that is the whole essence of like why these logical relations work. All right? Okay, so try out that case. Now, I guess I will be doing recursive types tomorrow, since we're kind of out of time. Are there any sort of other lingering questions in the last couple of minutes? Yes?
I don't think we ever got a definition of what logical relation is.
It is one of those things which is really hard to define. Okay, so if you try Googling like what this name means and where it comes from, there are all sorts of theories. So let me give you a little bit of history since we have a couple of minutes left. So the very first instance of logical relations goes back to 1967, I believe, or maybe 69. It's called Tate's method. They weren't called logical relations back then. And Tate used it to prove, I believe, normalization for simply type lambda calculus. It wasn't until a few years later when Gordon Plotkin was using this method, and he's not even sure that he's the first one to have coined it. He thinks maybe he used it because someone else was using this term. But you know, I think we trace it back to Gordon Plotkin. Some people say that they are logical relations because they're defined by induction on the type structure. So think Curry-Howard, think types like logic. So there's a sort of, you know, but I think that's a made-up explanation after the fact. But there's something to it. I actually like that one. Right? They are defined. They're in this sort of logical structure. And just to kind of see some more of that, so how would you define, suppose that I added pair types to this language. How would you define what values belong to a V relation at type tau 1 cross tau 2? So suppose that I have pairs, V1, V2 in my language, E1, E2, and I have first and second. Yeah, okay, well, I'm going to write it out even more like that. What terms do I put here? Okay, V1 comma V2, pairs. Okay, assuming that that's the syntactic form. I know I haven't put it up there. All right, and then we want to say that V1, V2 belong to this relation at the pair type, and now what you were saying, right? If and pair, right? Okay, V2 belongs to the V relation at V2, right? So this is some of where this, like, they're defined, you know, by induction on types, therefore based on the logical structure of types. Yeah, things like that. But you know, there are other interesting issues. I tried to sort of emphasize that you define these relations so that at various types, and I won't say at every type, but at various types, you want to make sure that the elimination form for the type preserves the relation. But notice how we only really saw that for lambda, for function types. The elimination form for function types is application, and the definition is saying something about exactly what happens when you do an application. See, it's built in. It's not really built in for Booleans, right? What's the elimination form for Booleans? If. Are you guys familiar with polarity? Has anyone talked about polarity, focusing here? Okay, then I'm not going to go there. Very briefly, did someone? Positive types, negative types? You know what function types, are they positive or negative? Okay, maybe I'm going into territory that maybe I shouldn't. I'll leave it at this. There are certain types which happen to be negative, where you will have to spell out exactly what happens with what the elimination form does. positive types, the ones on which the elimination form is doing a pattern matching, you normally don't have to say it. And I'm not going to say that this is a hard and fast rule. Use it as a guideline. Now, what's happening in pairs? Pairs, if your elimination form is first and second, right? So you have first to V and second to V. That's how you project something out of a pair. Then you could say that I am actually using the elimination form right here. Pairs, by the way, like functions, are negative. The elimination form is right here. I just haven't written it like that. Notice that V1 is exactly first of V1, V2. But I just sort of wrote it as, then I would have to write an E, right? But I just wrote it in this more, the content is the same of those two specifications. I'm just saying I'm writing in two different styles, right? So we could have written it as first of V1, the pair V1, V2, in E of tau. There. That definition should give you exactly the same specification as the thing that I just erased. So I'm saying that the elimination form, what the elimination form is doing with constructs of this type, with pairs, is built into the definition, just like it is for lambdas, even though when I write V1 and V tau 1 and V2 and V tau 2, it's hard to see that really, but it's there. Yeah?
What about if you have
Then won't work. And again, it's this guideline of polarity in the sense of these positive types have elimination forms where you pattern match. So sums are a good example. How would you define if you had in left, in right, and sum types tau 1 plus tau 2? The elimination form for those is a case expression. It's pattern matching again. A case expression, like an if-then-else expression, returns something of a completely different arbitrary type. If I tried to build that in, like, an if-then-else is a pattern matching thing too, right? Essentially. If I tried to say what happens when I do an if-then-else on this, what would happen? An if-then-else returns something else of an arbitrary type tau. Suddenly the induction on types is falling apart. I can't even say it and have an inductively well-defined logical relation, right? So this is just a hint of some of the issues that come up, all right? Normally we try to teach this without going into too much of this stuff. And we have developed guidelines for, hey, if you have a pair, you do this. If you have a function, you do this. If you have a sum, you do this, all right? And then when you start out especially, you follow the rules, and slowly it starts to become clear why you can't do certain things certain ways. But we can talk more about sums tomorrow, all right? Okay, we should probably stop now. All right, thank you.